So now that we've talked more about how to include two explanatory variables, we're going to extend that to looking at multiple explanatory variables. So we're going to build what's called a multiple logistic regression model. And multiple just means how many x's, or we're allowing for having multiple explanatory variables in our model. So there's different steps depending upon different classes that you take that someone may recommend for going through for model building. So you may have seen different steps in the ones I'm going to present here. These are the steps that I'm going to expect you to go through on like your homework assignment and stuff like that. So the first thing we're going to do is fit all possible one variable logistic regression models. What that means, we're only going to fit one x variable each time. We're just going to fit multiple one variable explanatory variable models. So we're going to do that for each of our possible variables that we're interested in. We're going to use a larger than normal significance level for our alpha. So from this x, when we fit that model, we're going to get a p-value that helps let us know if our variable x is useful in predicting our probability of success. From this p-value, we're going to compare that to 0.2. Anything less than 0.2, we're going to say, okay, we're going to look further into this variable. Anything larger than 0.2, we're not going to take that variable any further. So it's going to be kind of like a first screening process to see, does this explanatory variable have any potential of being useful in predicting our probability of success. Once we've done our first screening, we're going to put all these variables into a multiple logistic regression model, and we're going to perform backward elimination. So what backward elimination means is we're going to fit all of the variables and see which variable we would remove first. We're going to use a slightly different alpha now. We're going to make it a little bit tougher to keep a variable. We are only going to remove one variable at a time. So if you have multiple variables that don't seem to be significant, we can only remove one at a time. And the one that we're going to remove will have the largest p-value. Now again, as a reminder of why we're only going to be removing one at a time is when we look at those p-values, when we look at those hypothesis tests, it always assumes that all the other explanatory variables are in the model. And so if I remove one, that can affect the p-values of the others. So that's why we only want to remove one at a time. That's what we're going to do to build our multiple logistic regression model. If we were in a more advanced class, we'd be talking about adding quadratic and interaction terms. We would also be talking about assessing goodness of fit tests and just conditions in general to make sure that the model is a good fit. But again, we're not going to quite extend that far in this class. So we're going to do this for our example. So let's actually go back and just remember what our place kicking data set even looks like. So we had tons of variables. We haven't really talked through a ton about what each of them are, so we're going to do that here now. So week is just going to tell you which week in the NFL season it was. Distance we've used. Alt is going to give you the altitude of basically where the stadium is. Some people might believe if you're at, for example, the Mile High Stadium, that might have an effect on your ability of making a place kick. So we have altitude as a possible explanatory variable. Our home is going to be an indicator variable, which means it's just a 0 or a 1. 1 if it's a home game for that team, 0 if it's an away game for that team that's doing the kick. This type variable is going to let us know if we're playing in a dome or not. 0 is actually going to be for those that were a dome, and 1 will be in a non-dome. Precipitation, this precip is going to let us know if there was any type of precipitation coming down. 0 if there was no precipitation, and 1 if there was any precipitation, so rain or snow or something like that. Wind here was actually done as a binary variable of 0 and 1. 0 if your wind speed was less than 15 miles per hour, and 1 if the wind speed was above 15 miles per hour. This might have been more useful as a quantitative variable, but very hard to record the wind speed at every possible kick to get that information very easily. Change is a variable we've looked at before. So it was 0 if the resulting kick being made would not result in any type of lead change, versus 1 would mean that that team that was behind would now be either tied or ahead if they made the kick. Elap 30. So there's 30 minutes in each half of an NFL game. So it lets you know how much time has elapsed of those 30 minutes in the half. The PAT lets you know if the kick was a point after attempt or not. So it's going to be 0 if it's a field goal and 1 if it was a point after attempt. So for those that do not know, a field goal is worth 3 points and a point after attempt is only worth 1. So the number of points there will be different if the kick is successful or not. Field lets you know what kind of field that the team was playing on. This lets us know if it was grass or turf. 1 would denote that it was a grass field, and 0 would let you know that it was a turf field that it was played on. Good is our response variable. And then we have a temperature variable, like kind of know what temperature it was. Anything though that was considered inside of a dome, we used 72 degrees as its temperature. So very quick going through all those different explanatory variables that we had. But now what our goal is going to be is to fit each of those explanatory variables as our only explanatory variable to predict the probability of a place kick. And we're going to do that for each of them. So we're going to be fitting a whole bunch of models that look like this with only the explanatory variable changing each time. So for example, I've done it here with altitude being our explanatory variable. So when we run that, we're going to get a corresponding p-value here that we can look at to compare to 0.2 to again be that first screening of does it seem like altitude is going to be useful to me to predict the probability of a successful place kick. Since this p-value is relatively large, I would end up not using altitude in my next step. But now we're going to do this for all of the different explanatory variables. You do not have to do it this way, but I'm creating a function to be able to do this. So this little function I do here, I will put this code out for you as well, so if you want to just use it, you can. This is going to allow me to just use this function down here and just change the explanatory variable, but not have to rewrite out that other code all the time. The list variable, though, is going to be useful for me. This p is going to give me my p-value that I'm going to want to have to be spit out later. So that's why I'm asking to get that piece of information. So I'm going to fit it for all of my variables: altitude, change, distance, that type variable, home, point after attempt, precipitation, field, temperature, how much time's elapsed, and then the week. So we're going to do that here in R, so you can see what it actually looks like as well. So this is me creating my function. So this is the code I will give you guys. So that's not going to spit anything out. That's just creating my function there. Oops. And I need to run my last little line of it there so that my function is ended. So now I'm going to run it for each of the explanatory variables. Notice I'm storing it into something that looks a little bit like the variable name so that I remember which one is which. So running each of them here. And then I'm just going to pull off the p-value for each of them into a data frame here for me. So I can get all of those p-values in one place. So that's just trying to kind of make that very first step of doing the quick which of my variables is useful a little bit less time consuming here. So now actually looking at that output. So here I have each of my variables that I use as my x variable and their corresponding p-value. So what I'm looking for, again, is I'm using an alpha of 0.2 to compare these two. Anything smaller than 0.2, we're going to say, yes, I'm going to use that one in my next step. Anything greater than 0.2, we're not going to use. So we will be using our change variable. We will be using the distance variable. Type here is pretty close to that 0.2 cutoff, but technically since it's bigger, I won't use it here since I have enough other variables. Home, maybe surprisingly, is not going to be used. Point after attempt is going to be used because it's very, very small p-value of 0, rounded to 4 decimals here. Precipitation, not. Field, no. Temp, no. Elapsed 30, yes. The week, yes. And wind, yes. So I basically have 6 of the variables that I'm going to want to use. So I'm going to want to use the change variable. I'm going to want to use the distance variable. I'm going to want to use the point after attempt variable. We're going to want to use the elapsed 30 variable, the week variable, and the wind speed variable. So those 6 are what are going to continue on with me now to look at backward elimination. So again, so what I'm going to do is now fit my new model, but now I'm going to use all 6 of those variables. Remember that the plus sign goes between our different explanatory variables here. The order you list these in does not matter. It's just that's going to be the order they are spit out here, which remember then will be useful for if I'm doing some confidence intervals of knowing which coefficient or what estimated variance to be pulling off. So that's kind of where that part will be important for us later. Everything else is staying the same as we've seen before. And then I'm just spitting out that output by looking at its summary. So now I have all of these different p-values. And you notice that I've highlighted the elapsed 31. Because remember, now technically at this point, if I'm going back, we are going to be using this 10% cutoff to be looking at. So technically I see 1, 2, 3 variables that have a p-value greater than 0.1. But again, when I look at all of these p-values, they're assuming that everything else is in the model. So is wind useful if I use all 5 other variables? So even though these might look like I want to eliminate them as well, I only want to remove one thing at a time. This is my highest p-value that is also bigger than 0.1. So the first thing to go is going to be the elapsed 30. Now this p-value looks a lot different than the one we had up here for elapsed 30. But remember, this was if I only used that to predict the probability of a successful place kick. It seemed pretty useful. But now it's telling me if I'm using all of these other things, change, distance, point after attempt, week, and wind, I don't really need elapsed 30 as well. So now I'm going to run the same model where now I'm down to the 5 variables because elapsed 30 is no longer in my option choice. And then I'm going to spit out that output. So here's my new list of p-values. Now again, I'm looking for ones that are bigger than 0.1, which again, there were 2. Largest one is the week. So we're going to remove week from our model. So in our next step, now we're down to the 4 explanatory variables here. Here's our new output. So now looking at our coefficients, wind is actually the only one that is greater than 0.1. Some people are going to use a very, very hard cutoff and say, okay, I think we need to remove wind. it's pretty close to that 0.1 cutoff. So some people may also make the argument of, well, even though it's close to my cutoff, I think I'm going to keep it anyway. So you could decide to remove wind. You might decide to keep it. So since I have sort of removed wind as a question mark, I did also fit the model without wind. So we would have both sets of coefficients. But if I were to remove wind, I would be done at this point because all three of the p-values that are left are less than 0.1. Now notice when I've been looking at p-values, I'm only looking at the ones attached to the variables. I'm not even paying attention to the one attached to the intercept. And I never will pay attention to that one. I'm just looking at the other p-values. So at this point, we would be done with our model. Probably the big question is, would you want to keep wind or do you want to remove wind? So, I mean, you could really justify either way. So let's write out our equation in both ways so that we can see what it would look like. So if we did it without wind, so we did decide to remove it, we would just be using the output right from up here. So I'll kind of scroll where we can see it all at once. I would say then that my pi hat of x is going to be e to our intercept, and then putting in my different coefficients times their corresponding variable. So change distance and our PAT variable. There on top. And on the bottom, 1 plus the same thing from above. If instead we decided that we wanted to not, or actually wanted to include wind, so first we would be using the output then down here, so having all 4 of our variables, as well as the intercept now when we're writing out the actual equation. So then my pi hat of x would be e. There our intercept is 4.82403. Our coefficient for change is negative 0.32574. For distance is negative 0.08917 for distance. For PAT, it's a positive 1.06463. And then for wind, a negative 0.50636. And then over 1 plus what we just wrote. So you notice that the coefficients are a little bit different when you have that extra term there, but they're not drastically different. So that's what our model would look like. Again, you can either justify removing wind or keeping wind in my mind here. And at this point, all of those intervals that we've done could be done in the exact same way. So first is a little refresher of what I mean by that before we dive in and find some predicted values. Right, so here we talked about how to do some confidence intervals for the betas and for odds ratios when we had multiple explanatory variables, where we had to be careful of which coefficients to pull off. So that's where the order you list them in your model becomes important, so you know which element to pull off. Interpretation wise, we had to worry about that assuming things stay the same. Now we'd have more things that we would have to assume stayed the same. So finding those confidence intervals with the same idea. Same idea here with trying to find predicted values in their confidence intervals on those as well. So you could do all of those intervals in the same way that we did previously with just 2 explanatory variables. But so now let's take some time to use these models to find some predicted values by hand. All right, so when we do this, we have 3 or possibly 4 variables, depending upon which of our pi hat models we decide to use. We can plug in different things that are realistic to plug in. So you want to be careful of making sure that things do actually make sense of what you're using. So we'll talk through what I mean by that as we do a couple of examples here. So remember, change is if there's going to be a lead change. So let's maybe first work with one where we're going to have a lead change if this kick was successful. We're going to make the distance 35 yards. Now, point after attempts. Now, most point after attempts are around the 20-yard line, give or take, depending upon if there were penalties or something like that. So the chances that you're actually going to have a 35-yard point after attempt that would result in a lead change it probably is not the most realistic thing in the world. So more than likely this is going to be a field goal, which would be a 0. And then you can decide if you're going to have wind or not. So maybe let's have no big wind effect. Now, if I use my green predicted model from before here, that's going to exclude wind. But if I use the purple one, it's going to include wind. So we can plug these different values in. So for this first one, I'll kind of actually show you down here what this will look like. So for our green one on this first one, we're going to be plugging in we decided it was going to be a lead change, so we're going to plug in a 1 for that. We decided the distance was going to be 35 yards. And that it was not going to be a point after attempt. There is no wind with this one, so I don't have to worry about the wind variable over 1 plus what we find above. All right, so we can do that math, and we would get 3.761696303 over 4.761696303, which would give us a probability of about a 79% chance. Now we could do the same thing with our purple predicted equation where we're actually using the wind. Still plugging in, though, the same values for change being 1. $35 being our distance. Not being a point after attempt. And here we decided to use no wind, so we plug in 0 there. Over 1 plus the same thing from above. Doing that, we get 3.96434 over 4.96434, which gives us 0.7986 as our probability. So notice that there was not much of a difference in our estimated probabilities here, whether we used the wind model or the non-wind model. So we could plug in some different values then for change in distance and PAT in wind to see how that affects things. Let me put in my little values up here. So you could plug in some different values. So suppose this time you want to do, okay, still a lead change, but I want a much larger distance. Still going to be a field goal. And heck, the less time, let's put in wind and see what happens. So now plugging in those values, what would you get? Feel free to pause the video here and make sure you're doing things okay on your own as well. So this time you do actually get a pretty big difference between our estimated probabilities, without of course doing any confidence intervals, though I know it would be hard to tell if they're really significantly different from each other. So why do these turn out so much more different than the others? Well, this time we actually had, if we again look at our models, intercept's not very different, that's not very different, not too big of a difference between those. But as soon as I actually made this wind of 1, and this number here in the exponent already being a pretty small number, once I subtracted off this 0.50636, actually had a pretty big impact. But let's do one where maybe you're actually going to see that maybe even having that wind won't have quite as big of an impact. So for this one, let's do a non-lead change, a pretty short distance. Let's make it a point after attempt and give it some wind. Now find your predicted values. So this time my estimated probabilities with the model without the wind variable and with the wind variable, notice aren't having that big of a difference. So what you'll actually see as that exponent is smaller, go back here, as you're raising e to a smaller number, this is going to have a bigger impact. So what's going to result in this being a smaller number? Well, that would be, okay, if there's a lead change, but then also if there's a larger distance, and then if it's a field goal. So we can kind of see how this wind is going to have a larger impact when there's actually a wind speed for larger distances, for field goals, and for lead changes. So kind of like all those different things that this subtracting off that's for that smaller exponent is going to have a bigger impact on our probability of success here. So you can plug in some different values just to kind of see what you feel comfortable with. I figured a 25-yard point after attempt at least seemed reasonable there for me. So you could plug in some different values, but again, just make sure that it actually makes sense to be working with here as well. Email me if you have questions or have any concerns over anything that we've worked through so far. Again, with this one, you could really argue whether or not to keep wind. I mean, we can see it does have an impact for some probabilities, but again, you could also do confidence intervals there and see if those actually did overlap with each other as well. So that's some final notes down here. There are sometimes you might get a message that says parameter estimates have not converged or complete separation. So first, if you try a larger number of iterations, that can help with the convergence idea. The second message, though, this complete separation, happens if something perfectly separates it. So what that would mean is, for example, let's suppose that you're working with this change variable. And every single time that change was 1, the kick was missed 100% of the time. Versus every time that lead change was 0, we always made it. So if there's this complete separation that all lead changes resulted in an unsuccessful kick and all non-lead changes resulted in a successful click, that's what this means of this complete separation, is that that variable is perfectly separating it. And so we can't then end up really using that variable to predict. Otherwise, it's going to be all that you would use. Like, well, then if it's a lead change, you're not going to make it. 0% chance. And that's not really one of the goals. But that's just what that kind of error message that you would get would actually mean there. Again, remember, if you're trying to figure out maybe which model fits the best, you could always use the AIC. So if we wanted to, also to decide if we wanted to include that wind variable, we can go back here and look. Without wind, it's 781.26. And with wind, it's 780.76. So it is actually smaller. So that might give you a reason then to kind of then argue as well, oh, okay, I think I'm going to use the model with wind in it. So we can still use the same ideas to look at to decide which model maybe fits best. Of course, we still want to use those p-values though to help us making decisions as well.